No?
Yes.
Yes. You're Philippe. Go there. Andre.
Yes, thank you. So I will speak about the influence of a forest of trees, a forest of obstacle, on the stability of a granular layer on inclined plane. So this work has been done in Laboratoire FAS in Orsay, just near Paris, and with two Argentinian researchers in the context of a international associated laboratory between France and Argentina on physics and mechanics of fluids. So the context is, the question is, can we influence the flow of a real granular layer or granular flows, which can be rocks avalanche or snow avalanche, by natural vegetation or artificial obstacle network? And before showing you our results, I will just recall some previous results on the stability of a granular layer on a rough inclined plane. So two main, there have been many studies on that interesting problems, and I just recall you two main contributions of Olivier Pouliquin group and also Adrienne Daher and Stéphane Douady studies. And the systems was a little bit different. This is glass bead glued on a plane, and this is carpet velvet on a plane. And also the feeding experiment here is quite a little bit different, but the findings are quite the same. And in this configuration, this curve corresponds to the thickness of the granular layer that remains on a rough plane at a given angle theta. So it corresponds to the stopping curve. And in this configuration, we have also access to the starting curve, which correspond to the thickness of the layer at which an avalanche starts, and then the thickness decreases at a given angle, and the flow stops here, like this. So these both curves can be modeled by some empirical laws, and there are many empirical laws, but I just show you two of these classical laws that contains three parameters: theta 1, theta 2, and lambda. Theta 1 is the angle for which there is no more influence of the plane. So h, the thickness of the layer, tends towards infinity. Theta 2 is the angle at which the thickness of the layer tends towards 0, and lambda is a characteristic length, characteristic 8, that correspond to the decreasing of the height from this theta to this, from theta 1 to theta 2, and this decreasing function can be an exponential one or a hyperbolic one. It is not very important, but we have done the same kind of experiment with glass beads of different diameter on a plane covered by velvet cloth, and we use this sort of law. And what we find is that the characteristic length here is always of the order of the grain diameter, and so there are different curves depending on the diameter of the beads. So theta 1 and theta 2 may depend also on the diameter of the beads. And the function, the influence, here is the result for theta 1 and theta 2. So theta 1 is about constant, whatever the grain diameter, and theta 2 decreases when the grain diameter increases, and this is due that this is due to the constant roughness of the plane. So when the grain diameter increases, the roughness is less and less important, and so this angle decreases. And this show you that lambda, the characteristic length here, is very linear with the grain diameter. So this is the results for classical rough planes. And now I just show you some results about inclined Fakir plane. So this is real Fakir plane because we have experimentally in the laboratory used some planes with a forest of nails. These nails are of a diameter of 2 millimeters and with a spacing of 7 or 14 millimeters. And we also varied the grain diameter between 0.1 and about 1 millimeter. So there are many size ratios that are important. The spacing between the nail over the nail diameter are about 3 to 7. The ratio between the nail diameter to the grain of the diameter between about 1 to 15, and the number of grains that are between two neighboring nails are the range are from 4 to about 100. And so the results are here. So this is the curve for the starting curve and stopping curves. This is the curve without nails, any forest. And this is the two spacings that have been used. So the narrowest spacing. So what we can see is that there is a clear effect of a clear stabilization effect. So if we are at a given angle here, the thickness of the layer that can be that can remain on the plane clearly increases with the forest of nails, and at a given thickness, avalanches appears starting at the larger angle for the narrowest forest. The same effect can be observed for starting and stopping curves, and we can model also the curve by the same law that I have shown you before. But now you will see that theta 2, which is the angle for vanishing layer, is not affected, and it's obvious by the forest. Also lambda is not affected, but the only of the three parameters that is influenced by the forest is the angle of theta 1, which represents here this divergency. And I will show you the dependence. So I just plot here the difference between the angle theta 1 for a given forest relative to its value without forest, which I note theta 1 infinity as a function of the grain diameter, and this is for the two spacing delta, just these two curves. And what we can see is that this spacing increase linearly with the grain diameter. So before and to understand this, we can model the stability of a granular layer on an inclined Fourier plane. So if we write the force equilibrium for a superficial layer of thickness HS, which is about to start at a given angle theta 1, this is the driving gravity force, G sinus theta 1. This is the resisting force due to the friction of the layer with the grains, and this is an additional term which comes from the presence of the forest of nails of our trees. And in fact, this coefficient of friction is related to the tangent of the theta 1 angle without the forest. And now, how can we write this term? And we know that a granular flow exerts on one cylinder a force which is proportional to the thickness of the flow to the square, and proportional to the diameter of the cylinder. This is the results of Albert et al. That we have also seen this morning, also shown by François Guillard. And so what we can say is that the force of the granular flow on a cylinder forest, and so the force that a cylinder forest exerts on the grain flow, is this force on one cylinder times the number of cylinders, the number of trees per unit surface. And so when we do that, we can divide this by this, and so we can express that the evolution of this angle when the spacing varies, which is given by this angle at infinite spacing, so the classical value, plus an additional resisting term that is given by this expression. So the cylinder diameter, HS, which is the thickness of the granular layer, and the spacing square. And so we use the same modeling expression with just this expression here now. And what we see is the following. If I just already show you these curves, and what we see is that this term minus this term evolves as the grain, the diameter of the grains, and so what we can conclude is that the superficial thickness that is destabilized, that flows, is in fact not all the layer, but only a few grains, or just one grain, or a few grains. And so if we replace HS by dg, the grain diameter, and plot this difference as a function of this ratio, we see that all the data collapse on a master curve. And the question is now, where come from this flow localization? And I just recall you that this localization has been already observed in many systems, like for stationary flows, fluid flows on inclined pile. So and this team has measured this characteristic length for the exponential decrease of the velocity profile. And in rotating drums, this is a little bit different, but the same scaling, and also by diffusive left scattering with about 1 grain diameter. So in this forced stationary flow, there is a linear velocity profile followed by an exponential velocity decrease with a characteristic depth that correspond to about 1 grain diameter. And this localization was also observed for unstationary avalanche flows, where Courrèges-Dupont and co-workers have measured the instantaneous velocity profiles and have observed that this corresponds to a exponential velocity decrease with a characteristic length of about 1 or 2 grain diameter. And this also have been observed for the effect of lateral walls on pile stability. And if you try to model the stabilization of the pile by lateral walls, some model expression gives you also that this parameter that contains the avalanche thickness, the thickness of the granular layer that flows, and has been also found of an order of 1 grain diameter. So for conclusion, we see a clear stabilization of a granular layer by a forest of trees, and this seems to be to give some flow localization, and perhaps it will be useful for risk management of snow and or rock avalanches. And also, this may be related to stabilization of soil by vegetation, or the root system, by the root system. And now we are doing presently some experiments with continuous feeding to see the effect of forests of trees on granular flows. Thank you.
Just a clarification, in the case where you do not have vacuum trees, did you see several H-dot curves? Is that what I saw on the slide? Was that if so, was that dependent on the kinds of particles you had on the velvet cloth? Yeah,
yes.
This one, yeah.
Yes, clearly here this is for about 1 millimeter grain diameter, and then smaller diameter. And
so
yes, because this curve is comes from the roughness of the plane, and the roughness of the plane must be compared to the grain size.
Jim?
A lot of the particles you're using are really small. Did you have any trouble with cohesion or repeatability?
No, not so much. We have using diameter from about this kind of no clear effect of cohesion.
Would you use the same pattern on like it's always a array of regular array of nails? Do you think it has an effect if you had used another pattern, different crystalline pattern, or these other?
Yeah, the way. Yes, we have built a network with a regular pattern like that. Clearly, the direction of this pattern or the exact pattern may have an effect on the curve, but I think it is a second order, and I think it will be perhaps the same. It is difficult to build several several planes with this forest of nails. It is quite long.
Maybe one more.
I'm guessing that the nails were, the flow is completely under the height of the nails.
Yes,
You know what?
this is very large trees.
Okay. What would happen if the trees were less in height and say the flow is half the height? The trees are half the height of the flow, say. So they're still big, but the flow is slightly deeper than natural trees.
I think if the question is what happens when the grains are over the.
Slightly over.
I think if the granular layer is larger, the nails correspond to a roughness, a strong roughness, a strong velvet carpet for a fakir man.
But will you have a stock layer up to the top of the nails and then a flowing layer?
A Stokes layer?
A stock, an immobile layer up to the top of the nails and then a flowing layer over it?
Yeah, maybe.
Yeah, exactly.
Yeah, maybe.
Okay, let's thank our speaker.